Good day, ladies and gentlemen. Welcome to my channel. Today I discuss symmetrical faults in power systems.
Every single day, I'm gonna make something great. That's my way.
Now, when we look at symmetrical faults, initially we need to define what a fault is. And usually a fault is an unintentional created conducting path that may be due to a short circuit or a blockage, which we call a blockage of current, which we call an open circuit. Now, most of the faults on the power system lead to what we call a short circuit. And there are various faults that can occur from the short circuit itself. You have got the open circuit and also grounding. We'll look at those shortly. But in any way, short circuit current determination is an important aspect for an electrical engineer because it is what is used to determine the equipment ratings and equipment selection from circuit breakers to fuses in the system. So without the knowledge of how to calculate short circuit currents, then an electrical engineer is going to struggle to design a system and arrange components and equipment in that power system. So it's a very important aspect. Our focus on this discussion is symmetrical faults. And what is a symmetrical fault? Basically, a symmetrical fault is a fault that brings about an equal fault current, which is 120 degrees apart in a three-phase system. So you've got these equal currents separated by 120 degrees in the system. Like we already mentioned, causes of faults, causes of short circuits include in a power system mainly equipment installation failure. This can lead to a direct short circuit, which of course could also be caused by lightning or switching stages. Then you have installation contamination, which occurs mainly due to pollution or salty sprays in the system. Then mechanical accidents may occur. A tree falling onto the power line, for instance, can cause a short in the system. A vehicle colliding into the power towers or poles, birds or animals shorting out lines. These are some of the causes of short circuits. But there are effects of short circuits, and these effects may be deadly in some cases, especially for personnel. That's why we have to consider that when there's a short circuit, there's a huge amount of current that flows through the system, and that huge amount of current can cause fire, which can injure personnel that are close to that equipment, because the thermal damage that is caused to equipment may actually lead to fire when two wires are touching each other. Then windings and bus bars may also suffer mechanical damage. This may be due to high magnetic forces caused by the high faulty currents. And then, as I mentioned, you can have injury to personnel through arc flashes, electrocution, or fires. And these effects are not wanted because equipment and personnel both have to be safeguarded. Looking at a graphical representation of the symmetrical faults or causes of faults, mainly what causes faults here, as you can see, is lightning. This is very common, especially in areas where the ground is highly conductive. You've got tree contact. That's why in many areas you have the utility company have to go around to trim the trees around the power lines and other areas. Then there's equipment failure. which, as we mentioned, could be due to failure of insulation. There's animal, of course, which can go into or cause short circuits between lines. There's wind. In highly windy areas, the wind can swing the power lines and cause about contact of the lines. Then there's digging, where people want to dig in, or there's a project going on where cables may be cut or cables may be forced to connect and cause a short circuit. Vehicle accident, snow, and so on. Vandalism is another area. Theft, people want to steal cables, can cause about short circuit faults. So these are causes of these, and usually for to protect against some of these, you have to have animal guards, for instance, line separators to avoid the lines touching each other during the wind, protecting from vandalism. If we define a short circuit, as you can see, we are saying a short circuit is based when two bare conductors touch each other, you create a short circuit occurs. Also, any abnormal connection can be arcing that can come from one conducting element to another element and cause about a short circuit. Now, the characteristics of a short circuit are that resistance drops to almost zero. So this increases the flow of current in that conductor, which makes it extremely high. And the voltage at the fault point is also reduced to almost zero. In a graphical representation, this is what we mean. If you have a fault between two lines, you've got the impedance, the voltage coming almost zero, and the impedance gets to almost zero. Other things that could cause, or other faults that could cause short circuit are faults such as overload. Overloading of a device can lead to overheating, which in turn can lead to insulation failure or insulation burnout, leading to conductors touching each other and leading to a short circuit. So mostly overload activities as well as ground faults, which can also lead to a short circuit condition. So mostly in most industrial operations, the common fault that you're going to see is the short circuit fault condition. And as you can see, a ground fault overload can all lead later on to a short circuit condition. That's why it's important to understand those important faults as well. When we look at a symmetrical fault, like we said, the symmetrical fault occurs only when the three conductors of the three-phase lines are brought together as shown here. So what you see is that when all these three conductors are brought to a short circuit, they are going to have equal currents. So the current in the red phase, the current in the yellow phase, and the current in the blue phase are all going to be equal in magnitude, and they are going to have a displacement of 120 degrees apart. So we are saying we are going to have the currents having 120 degrees apart. So there will be 120, 120, which means it's a balanced fault, which implies that the angles are equal and also the magnitudes are equal. Then also you must understand that since we are dealing with a balanced three-phase fault system, which has equal angles of displacement, then we can handle this situation by calculating simply a phase or a line to a neutral basis. So we can use what we call the per phase analysis, and this can work out for our calculations. Symmetrical faults are the most severe faults that can occur on a system, but it is a rare fault. What limits the fault in this case is what we need to understand. Firstly, you need to understand that the system, the impedance, is a combination of the resistance plus the reactance. In a system, what limits the fault current? And we are saying the impedance in generators, in transformers, and in the lines will limit the current. But in a case where the fault currents, like we mentioned, may be largely reactive, especially if the reactance, the total reactance in the system exceeds 3 times that of the resistance, then resistance is neglected. So what remains of the impedance is simply the reactance. And this is an important point for analysis, because in our calculation, then we have to focus mainly on the reactance as the form of impedance that limits the current. So if you have a fault at point F, then you have to consider the reactance of the generator, the reactance of the transformer, and the reactance of the line. And those reactances have to be summed up to come up with a total reactance. Total reactance, which should be the reactance of the generator plus the reactance of the transformer plus the reactance of the line. And this forms the total reactance that is limiting the flow of current up to this point of fault. So when it comes to reactance, we have to understand that we have to now calculate what we call the percentage reactance. So the reactance of transformers, generators, reactors, etc. are usually considered in what we call the percentage reactance. What is a percentage reactance? This is simply the percentage of the total phase voltage dropped in the circuit when full load current is flowing. So percentage reactance is calculated as follows. You've got the full load current multiplied by the reactance in ohms per phase over the phase voltage multiplied by 100%. So this gives you what we call the percentage reactance of a system. The advantage of using the percentage reactance is that it remains unchanged as it is referred through transformers, unlike ohmic reactances, which become multiplied or divided by the square of the transformation ratio. So the transformation ratio does not affect the percentage reactance, and this makes it easier to do calculations in the power system. When we look at percentage reactance expressed in kilovolt amperes or KVA, we express the expression of the percentage reaction is going to be the KVA multiplied by the reactance in ohms or ohms per phase over 10 multiplied by the kV squared. This is what you obtain when you calculate the percentage reactance in KVA. So the short circuit current, therefore, the short circuit current, which is ISC, is going to be equal to the voltage over the reactance. But we are interested in finding the percentage reactance in using or replacing the ohmic reactance by using the percentage reactance. So if we go back to this formula, we want to replace this ohmic reactance by the percentage reactance. And for this reason, we have to place back into this equation for the short circuit current, and it leads us to obtaining the short circuit current to be calculated by the full load current multiplied by 100 over the percentage reactance in the system. So this is what we obtain as the formula for finding the short circuit current in the system. If we look at a small example, for instance, if you are to calculate the short circuit current of an element, if its percentage reactance is 20% and the full load current is 50%. So using the formula that we demonstrated, we're simply saying the short circuit current is equal to the full load current multiplied by 100 over the percentage reactance. In this case, the percentage reactance has been given as 20%. The full load current has been given as 50. So it's simply 50 multiplied by 100 over 20, which gives us 250 amps. Bear in mind that this applies to this element if it's the only element in the system. If there are many elements, then you have to get the total reactance in the system up to the point where the fault has occurred in the line. What is the advantage? Like I mentioned, the advantage of using the percentage reactance is that, first of all, it makes the procedure simple and permits quick calculations because its value, the percentage reactance, remains unchanged through transformers. Whereas if you use the ohmic reactance, then it is going to be affected by the transformation ratio, which you are either going to divide by or multiply by that. So this is an important aspect to note. In most cases, we use the calculations that we obtain, we follow or use what we call as the base KVA, because most of the equipment, generally various equipments used in the power system, have different KVA ratings. It is important that we find the percentage reactance of all the elements on a common KVA rating. This common KVA rating is called the base KVA rating, and this is what we are calling here the base KVA. So to obtain the base KVA reactance is that we get the percentage reactance at base KVA to be equal to the base KVA that you choose over the rated KVA multiplied by the percentage reactance at the rated KVA. And bear in mind that this KVA is an arbitrary value, meaning you can select whatever value you prefer based on the system you're dealing with. For example, you are to calculate the percentage reactance using a base KVA of 2000 KVA for a 1000 KVA transformer with 5% reactance. So the percentage reactance at base KVA is going to be equal to the base KVA that you have chosen over the KVA rating of that transformer multiplied by the percentage reactance of that transformer, which in this case gives us 10%. Now, if we are to look at the why this base KVA is doesn't matter what you choose, let's look at this example. So you've got a three-phase transmission line shown below, operating at 66 kV, connected through a 1000 kVA transformer with 5% reactance to a generating station bus bar. The generator is 2500 kVA with 10% reactance. This as shown on the diagram. And what we are being asked is to find the short circuit current if you are using different KVA, base KVA ratings. Let's look at this system. Let's say we are using a base KVA base of, let's take 2500 kVA. Okay, and now we have to calculate the short circuit current in the system, and we know that first of all we have to calculate the transformer reactance at base, so we have to transform all the percentage reactances to the base KVA. So if we look at a transformer, its reactance, percentage reactance at base KVA is going to be equal to, we've got 2500 over the transformer rating multiplied by the percentage, which is 5%. And this will give us 12.5%. Now, similarly, we get to the generator. So the generator percentage reactance is going to be equal to the base KVA, which is 2500, over the rating of that generator multiplied by its percentage, which is 10%. So this is going to give us basically 10%. And therefore, our total reactance is going to be equal to 12.5 plus 10, which will give us 22.5%. From there, we have to determine the full load current at 2500 kVA base at 66 kV line voltage. So the current, full load current is going to be the base KVA multiplied by 1000. So we're changing it to just volt amperes over root 3 multiplied by the voltage multiplied by 1000. This gives us 21.87 amps. Now, this is our full load current that we have in the system. So the short circuit current, therefore, can be solved by the formula, the full load current multiplied by 100 over the percentage reactance, which in this case is 21.87 multiplied by 100 over the percentage reactance, which we found to be 22.5. And this gives us the short circuit current of 97.2 amps. Okay. Now, the same scenario. Let's pick a base KVA that is different. A base KVA of, let's say, of 5000. So 5000 kVA is now our base KVA. And then from there, we begin the same. The transformer reactance is going to be equal to, so that is the reactance, percentage reactance at base KVA is going to be 5000 over the transformer rating of 1000 multiplied by its percentage, and this gives us a value of 25%. And then we go to the generator percentage reactance at KVA, at base KVA, which is going to be 5000 over 2500 multiplied by 10%. And this gives us 20%. And the total percentage reactance at base KVA is going to be 25 plus 20, which gives us 45%. And from there, we calculate the current, the full load current, which is 5000, which is the base KVA, multiplied by 1000 over root 3 multiplied by 66 by 1000. This leads or gives us 43.74 amps as the full load current. Then from there, we determine our short circuit current. So our short circuit current is going to be equal to I by 100 over the percentage reactance. And our I is 43.74 multiplied by 100 over the percentage reaction, which is 45%. And this gives us the short circuit current to be equal to 97.2 amps, which is the same as what we found in the previous. So it doesn't matter what base KVA that you choose, you're still going to get the same result in terms of the short circuit current. And this is what we had obtained. This is what we had obtained in the previous example, when in the previous selection of the base KVA of 2500 KVA. So the symmetrical faults in terms of KVA, then we have to consider the calculation of that KVA short circuit current in terms of KVA because of the ratings of the system. So we are saying the product of normal system voltage and short circuit current at the point of fault expressed in KVA is known as the short circuit KVA. And to obtain this, we are saying taking the normal voltage, the normal phase voltage as V in volts and the full load current as I, amperes at base KVA, the percentage reactance of the system KVA up to the fault point, and then we know that to find the short circuit current using the percentage reaction, we use this formula. Now, if we replace this percentage the short circuit current by this formula into this equation, then we obtain the short circuit current in KVA to be equal to the base KVA multiplied by 100 over percentage reactance. And this still shows us that you still obtain the same result as the previous example that we looked at. So in the previous example, we had selected the base KVA of 2500. If you multiply that by 100 over the percentage reactance there was 22.5, you will get roughly 11,101.11 KVA, which in the same scenario, if you pick 5,000 multiplied by 100 over the percentage reaction was 45, this is going to give you 11,101 111.11 kVA of current. So this proves that the base KVA does not matter. You still get the same result. So reactors are used to control the short circuit currents, and in many cases additional reactors are installed in the system on various points. The reasons that the advantages of using reactors in the system are that reactors limit the flow of short circuit current and therefore protect equipment from overheating as well as from failure due to destructive mechanical forces. Also, most faults are localized or isolated and does not affect the other elements of the power system, which increases the chance of continuity of supply to the system. Then installation of circuit breakers of lower rating is a possibility because you've got the higher currents controlled or limited by the reactors. So therefore, you can choose circuit breakers of lower rating, which in turn reduces the cost of operation of your system. Reactors can be installed on various positions in the system. The first position that we look at is the installation of reactors in series with the generator, and we call this generator reactors. These systems do have their own disadvantages. Mostly is that there's a constant voltage drop and power loss in the reactors during normal, even during normal operation. And then if the bus bar feeder or fault occurs close to the bus bar, the voltage at the bus bar will be reduced to a low value. So the voltage in the bus bar will be affected when there's a fault that is closer to the bus bar. For instance, if a fault occurs at this point. So, and then a fault occurs on a feeder, the continuity of supply to other is likely to be affected. So if there's a fault on a feeder, then you have effects on the continuity of these other feeders because the whole busbar system may be affected. Then we come to what we call the feeder reactors. Now, the feeder reactors are reactors that are placed in series in the feeders. And there are a number of advantages. First of all, the faults are localized in terms of the feeders. If so, there's a fault on this feeder, if there's a fault on this feeder, this particular feeder, then what you're going to have is only this feeder is going to be affected and the customers on this feeder. Then if a fault occurs on any feeder, the voltage drop in its reactor will not affect the bus bar voltage. So the generators will not go out of synchronism. They'll stay synchronized because the bus bar voltage will not be affected much. This is the advantage of having the having the reactors in the feeders. The advantages though is that still the same disadvantage that you experience in the first in the first scenario when you have the feeders in the generator also occurs here. So what happens is that just as in the generator reactors, there is a constant voltage drop and power loss in the reactors even during normal operation. And then if a short circuit occurs at the bus bars, no protection is provided to the generators. However, this does not affect the generators, modern generators much, because modern generators have got sufficient leakage reactance to enable them withstand short circuit currents across their terminals. And then the other disadvantage is that if the number of generators is increased, the number of feeder reactors will have to be increased to keep the short circuit currents within the ratings of the feeder circuit. The last component of installation is what we call the busbar reactors. Busbar reactors is when you have the two systems that can work. One is what we call the ring system reactors. In the ring system reactors, instead of bus couplers in this bus, the bus couplers are replaced by reactors, and these reactors connect the bus bars. This implies that one feeder is fed from one generator. So you've got this feeder being fed direct from one generator, and these are the systems that are created like so. And because of that, you've got the advantages that there's the fault that is very common to the generator reactor and also the feeder reactor is minimized or completely eliminated. And this is what we are saying. So Reactors in the bus bars overcome the disadvantage of considering voltage drop and power loss in the reactors during normal operation. This is what happens in the first two cases that I showed. Then the other setup that could be done is by creating or installing what we call the tie bar reactor. So this reactor is placed with an additional tie bus bar. So this becomes a slight disadvantage of this system because you need an additional tie bar, which is a cost to the system. But in any case, additional reactors, additional generators can be added to this system without the change of the reactors. So an additional generator can be added to the system and it will still work just as fine. The location of reactors, three methods that can be used, and these are the three methods that we have discussed. The steps to solving now symmetrical fault calculations, as mentioned, about 6 steps. The first step is for you to draw a single line diagram, just like we showed in the example, to assist you to indicate all the voltage percentage reactances of each element. And also you have to choose a numerically convenient base KVA, select a base KVA, and then convert all the percentage reactances to this base KVA. Corresponding to a single line diagram of the network, you have to draw a reactance diagram showing one phase of the system and the neutral, and indicate the percentage reactances on the base KVA in the diagram. That will assist you to now calculate the short circuit current. Additionally, you have to find the total reactance of the network up to the point of the fault, and let that be the percentage reactance total. And then you find the full load current I using the selected base KVA. Then the various short circuit calculations can be obtained using these two formulas, which I have demonstrated before. And this is how you are going to solve for the short circuit currents. I'll run you through in the next video. I'll show you the examples of how we calculate symmetrical faults. Thank you for listening, and please don't forget to subscribe to the channel. Hit the bell for notifications, and subscribe for more, as I will run you through many more topics and interesting facts. Thank you. My dear friends, thank you for watching this channel. Subscribe to the channel for more. Thank you. Have a good day.